A binomial probability distribution describes the behavior of a discrete random variable, such as rolling a die, choosing a card. The conditions for a distribution to be binomial are that there is a fixed number of trials. Each of those trials has two possible outcomes, success or failure. The probability of success is constant, and that the trials are independent of one another, meaning that the outcome of one trial does not impact on the outcome of another. So for example, let's take a biased coin, where the probability of getting heads is 1/4, and the probability of tails is 3/4. And if we look at 3 trials, 1, 2, 3, the probabilities of those don't change from one trial to another. So on the second trial, it's still a 1/4 chance of getting heads and a 3/4 chance of getting tails. So from that, we know how to work out the probability of different outcomes. So the probability of 3 heads is equal to 1/4 times 1/4 times 1/4. The probability of heads on the first 2, followed by tails, is 1/4 times 1/4 times 3/4. If we generalize that to look at the probability of 2 heads occurring, then we have multiple ways of that happening. We can go heads, heads, tails. We can go heads, tails, heads. Or we can go tails, heads, heads. Each of those is 1/4 times 1/4 times 3/4, just in a slightly different order. So if we were to generalize the probability of getting 2 heads, that would be 1/4 times 1/4 times 3/4 multiplied by 3. And we could continue on with that, and we would end up with the following probability distribution. Okay, and this is what's referred to as a binomial probability distribution. The probability of 3 heads is 1 in 64, 2 heads is 9 in 64, 1 head, 27 in 64, 0 heads, 27 in 64. So that's a binomial distribution for this particular coin. What we want to look at is generalizing this. And what the binomial distribution allows us to do is calculate fairly easily the probability of the number of successes in 10 different trials, or 20, or 30, by generalizing this. So if we think of flipping heads as a success, then what we're dealing with in the first instance is that the probability of 3 successes being flipping heads is 1/4 times 1/4 times 1/4, basically 1/4 cubed. If we look at the probability of 2 successes, then that's 3 lots of 1/4 squared times 3/4. 1 success is 3 times 1/4 times 3/4 squared, and the probability of no successes is 3/4 cubed. 3/4 times 3/4 times 3/4. Let's do some generalizing here. X is a successful event, flipping heads. So let's change this to say x equals 3. And let's change the probability to p, the probability of success. In this case, the number of successes we're now interested in is 2. the probability of success is P, and the probability of failure is 1 minus P, because success and failure are complementary. And then we've got x equals 1 and x equals 0, and if we do the same substitutions, we end up with this. The last thing we want to generalize is where this 3 comes from. Basically, this is the number of ways we can choose, or we can have 2 successes out of 3 trials. This is the number of ways we can have, this is the number of ways we can have 1 success out of 3 trials. And there is a value in these that's the same. Basically, here we're looking at how many ways we can have 3 successes, which of course is 1. So to summarize all of this, we can come up with this generalization. So the number of ways we can have or choose those particular number of successes from our number of trials, n. So the number of ways we can have r successes out of n trials is n choose r times the probability of success multiplied by the number of successes times the probability of failure multiplied by the number of failures. Just to summarize this, the way we can express that something is binomially distributed is using this notation, which simply means x is binomially distributed with n trials and a probability of success p. The final 2 formulae here are for the expected outcome, which is the number of trials times the probability of success, and that makes sense, right? If we know we have a 50% chance of success and we do 100 trials, we would expect to have 50 successful outcomes. It's just a generalization of that, and the variance is the number of trials times the probability of success times the probability of failure, and that's simply a measure of spread. I'd like to look at applying each of these different formulae. So what we have here is a 6-sided die, and it's biased such that a 2 will occur 25% of the time. And the die is rolled 10 times, and we have to find some different probabilities. So the probability of getting a 2 on the first 3 rolls only, this is one particular scenario. This probability is simply the probability of getting a 2 on the first roll, multiplied by a 2 on the second roll, multiplied by a 2 on the third roll. Now that can all be simplified to 0.25 cubed, multiplied by the probability of getting something other than a 2, which is 3/4, and that's on the next 7 rolls. That can be generalized to that. Okay, and we just multiply those together. Very small probability, 0.209%. With question 2 and 3, what we're now looking at are scenarios where there are lots of different outcomes. So in the first example, there was literally only one way that we could achieve that, and that was by throwing a 2, followed by a 2, followed by a 2, followed by 7 outcomes that were not 2s. In the second question here, what we're trying to find is the probability of exactly 3 2s, which means we want 3 successes. We can apply this rule. And so what we get is the number of trials, the number of successes. So this will tell us how many ways we can have 3 successes out of 10 trials, multiplied by the probability of success to the power of the number of successes multiplied by the probability of failure to the number of failures. And so what we have is the same probability we calculated in 1, but multiple different ways of achieving that. On your GDC, remember we can do N choose R going through menu, probability, combinations. And then we simply go 10, 3. What that means is that there are 120 different combinations where we can have 3 successes from 10 trials. And so with that, we would multiply our answer from part 1 by 120, which is 0.250. And we want 3 significant figures. Now, of course, that looks like it's the same as this. That's a coincidence in this question. If you look back at the exact value, or the more significant figures produced by the calculator, in this third question, what we want is at least 3 2s. Every time you do one of these, you want to write a probability statement. So the probability of x being greater than or equal to 3, at least 3 means 3 or more, so we must include the 3. There are a number of ways in which this can be done. We could do the probability that x is 3 plus the probability that x is 4, etc. But that's very, very time consuming, and we would have to do this for 3 successes, 4 successes, 5 successes, and so on, all the way up to 10 successes. We could also look at the idea that we could do 1 minus the probability of 2 or less. But that would still require for this one working out the probability that x is 0, 1, or 2. Still very time consuming. There is an option on your GDC that allows you to do that fairly straightforward. If you go into menu, probability, distributions, and you go down to these options here, we can calculate this without worrying about the formula. So for this particular question, we would choose CDF. What this one does is allow us to do a cumulative distribution and add the number of successes or the probabilities of each number of success together. So we can enter a lower bound and an upper bound and look at all of those. So what we've got happening here is 10 trials where the probability of success is 0.25, and we want to add together the probability of 3 successes, 4 successes, 5 successes, and so on, all the way up to getting 10 successes. And if we hit enter, in terms of the working out that you would show, you would write down that, exactly as it appears on your screen. Binom CDF, 10 trials, probability of success is 0.25, and we're cumulating from 3 to 10 successes, which is approximately 0.474. We can also do this first one using our calculator by going Binomial Pdf. What that does is allow us to look at a single success without cumulating it. So we still go through distributions, and we choose this option here, Binomial Pdf, where we have 10 trials with a probability of success of 0.25, and we're looking at 3 successful outcomes occurring, which you can see is exactly what we got when we did it using the formula. And for that one, your working out would be Binomial Pdf 10, 0.25, 3. So Binomial Pdf and CDF, very useful in saving you time. So we can also use this in more complicated scenarios. So what we have here is a question where we want to know a certain probability, but we do not know the number of trials. So in terms of starting this off, I would begin with a probability statement. So what it says is we want to get at least 1, 2. So the probability of rolling at least 1, 2 would be written like that. And we want that to be greater than 0.9. So that's what we're looking to do. I'm going to first discuss the issue with this. And the issue with this is that if we want to do this, we'd have to go Binom CDF. We don't know the number of trials. The probability of success, still 0.25. And we want to go from 2 to n. Now that's problematic because we have an unknown in there. Sorry, at least 1, 2. So what we have to do with this then is think about a way around it. If we think about how many successes there can be, we're doing n trials. So we can have no success, 1 success, 2, 3, 4, all the way up to n. What we're after is the probability that we have 1 or more successes. That excludes the probability of having 0 successes. The probability of having at least 1 success and having no successes, complementary. So that adds to 1, which means we can rewrite this problematic statement as 1 minus the probability that x is 0 successes. This is quite straightforward to work out. It's n choose 0 multiplied by the probability of success to the power of 0 times the probability of failure to the power of n. And that has to be greater than 0.9. This is 1, this is 1, and so 1 minus 0.75 to the power of n must be greater than 0.9. This is now something that we can solve. We just need to be careful with the inequality. So, working through and solving this, we subtract 1 from both sides. We divide by -1. At this point, being very careful to flip the inequality. We now write this in log form. Log to base 0.75 of 0.1 is less than n. And then, because we want n as the subject, we have to flip that inequality again. The question, remember, said what is the largest number of rolls, which is actually an error. It should say the smallest number of rolls, such that that probability is greater than 0.9. And so we're going to end up with an n is greater than, which will give us a minimum value. Okay, so there's the answer we get when we do the calculation. It tells us that n must be greater than 8.0039. That's important because in this context, we have to round up to 9. 8 trials would not be sufficient. So n must be greater than 9. 9 is the smallest number of trials. The expected number of 2s is simply the number of trials, and if we refer back to the initial scenario where there were 10 trials, it's n times the probability of success, 2.5, and you can have a decimal here. The variance is n times p times q. N is 10, P is 0.25. Q is the probability of failure, so 1 minus P, which is 0.75. 1.875.